It still holds every record, 50 years later. Fastest air-breathing aircraft ever built. Fastest jet ever to cross North America. Highest sustained altitude of any operational aircraft in history. Mach 3.2, that's roughly 2,200 miles per hour. New York to London in under 2 hours. And not a single aircraft designed after it has beaten those numbers. That isn't a story about nationalism or Cold War bravado. That's a story about engineering so extreme it created its own category, and then quietly closed the door behind it. This is the machine, and this is how it actually worked. Let's start with the problem that almost killed the program before it began. When Kelly Johnson and his team at Lockheed's Skunk Works sat down to design what would become the SR-71, they ran into a wall that no engineer had ever hit before at this scale: heat. At Mach 3, air friction doesn't just warm an aircraft's skin, it cooks it. Leading edges reach over 600 degrees Fahrenheit. The nose cone pushes past 1,000. Aluminium, the material that builds virtually every other aircraft, melts at around 1,220 degrees Fahrenheit. It would have been structurally useless before the SR-71 even reached cruise speed. Steel could take the heat, but steel is dense, and an aircraft made of steel would be too heavy to reach the altitude and speed the mission demanded. The answer was titanium, a metal with the strength of steel, the heat resistance to survive Mach 3, and roughly half the weight. Sounds elegant, it was a nightmare. In the early 1960s, nobody had built a large aircraft from titanium because nobody had figured out how to manufacture it at scale. Standard machine tools blunted instantly. Cadmium-plated fasteners corroded the metal on contact. Early test panels cracked and failed for months before anyone understood why. The culprit? Chlorine in the tap water used to clean the parts. Titanium and chlorine react. The Skunk Works team had to switch to distilled water. Even the ink in certain felt-tip pens contained enough chlorine to initiate cracking in titanium structural members. Pens were banned from the shop floor. This was not an aircraft being built with existing knowledge. Every step of its construction required the industry to invent new manufacturing methods from scratch. 93% of the SR-71's airframe, by weight, is titanium. That number alone tells you how serious the thermal problem was. But the material choice was only the beginning. The shape itself had to be engineered specifically around heat. Those long, flat, blended body extensions running along either side of the fuselage were not purely aesthetic. They generated controlled lift at supersonic speeds and reduced aerodynamic heating on critical structural points. The aircraft's own shape was managing heat distribution, form and thermal engineering unified. There is one more consequence of that heat that most people never consider. The SR-71 leaked, not through failure, through intent. On the ground, the aircraft sat in ambient temperature. Titanium, like all metals, contracts when cold. The fuel tank panels were designed with gaps between them deliberately, because at cruise temperature and speed, those panels would expand to form a perfect seal. Build it tight on the ground, and at Mach 3, the airframe buckles. So every SR-71 that ever flew took off trailing fuel, then refueled immediately from a tanker once it reached operational temperature. The thermal expansion of the airframe was not an engineering flaw they accepted, it was an engineering constraint they designed around. That distinction is everything. Now, let's go to the engines, because the J58 is where the engineering becomes genuinely otherworldly. The Pratt & Whitney J58. To this day, the only engine ever designed to operate continuously in full afterburner as its normal cruise state. Every other jet engine uses afterburner as a brief emergency boost, a few minutes maximum. The J58 ran there for hours. That single fact defines how different this engine was. But here's the more remarkable part. At Mach 3, the J58 didn't really function like a turbojet anymore. Below Mach 1.7, it operated as a conventional turbojet. Air compressed by the compressor stages, combustion, thrust. Standard cycle. But as the aircraft pushed past Mach 2, the incoming air was moving so fast that the compressor became a liability rather than an asset. Ram pressure, the sheer force of air slamming into the inlet, was generating more compression energy than the compressor itself could add usefully. So the engine bypassed most of the compressor. 6 bleed tubes routed air around the compressor stages and straight into the afterburner section. At full cruise, the J58 had effectively converted itself into a ramjet, an engine with no moving compression parts, wrapped inside the skeleton of a turbojet. No other operational engine in history has ever done this. A single power plant that dynamically reconfigured its own thermodynamic cycle depending on flight speed. And the inlet system, the spike-shaped cone at the front of each engine nacelle, was as important as the engine itself. At Mach 3, the air entering the engine is supersonic. You cannot feed supersonic air directly into a combustor. It has to be slowed to subsonic speeds first, or the combustion process becomes uncontrollable. The inlet spike managed a series of precisely positioned shock waves, controlled compressions in the air that slowed and pressurized the incoming flow. Get the position wrong by a fraction, and the engine would unstart. A violent shockwave reversal that could slam the aircraft sideways hard enough to disorient the crew. An unstart was described by SR-71 pilots as being hit by a truck from the side, suddenly, at 80,000 feet. The inlet control system had to move that spike automatically, in real time, based on speed, altitude, and temperature, maintaining the shockwave in exactly the right position at all times. It was an analog flight control problem of extraordinary precision. Now consider this: 2 engines, 2 inlet spikes, each managing its own shockwave independently on an airframe doing over 1/3 of a mile per second. This had to work, all the time, automatically. The inlet system alone generated more thrust than the turbojet core at cruise. That is how dominant ram compression becomes at Mach 3. Let's go back to heat, because we need to understand it fully, not just as a materials problem, but as an operational environment the crew had to survive inside. SR-71 pilots wore full pressure suits, functionally identical to spacesuits, because at 85,000 feet, a cockpit breach means instant incapacitation. The atmosphere at that altitude is effectively vacuum. The cockpit itself reached temperatures that required active cooling. The windscreen, made from quartz rather than standard aircraft glass, reached 600 degrees Fahrenheit on its outer surface during cruise. Pilots reported you could feel the heat radiating from the windscreen through your gloves. The aircraft's fuel, a specially formulated kerosene called JP7, was engineered to have an exceptionally high flash point specifically because it was going to be stored in tanks surrounded by a 600-degree airframe. JP7 was so thermally stable that you could drop a lit match into it and it wouldn't ignite. It required a chemical ignition additive, triethylborane, just to start combustion in the engine. Triethylborane ignites spontaneously on contact with air, producing that distinctive green flame you see in SR-71 engine start footage, one of the more striking details in the program's entire operational history. But JP7's role went beyond fuel. It was the primary coolant for the aircraft's systems. Hydraulics, avionics, environmental control, all shed heat into the fuel before it reached the engine. The fuel arrived at the combustor preheated by the aircraft's own systems. That preheating actually improved combustion efficiency. The heat that threatened to destroy the machine was simultaneously being harvested to run it. This is what sets the SR-71's engineering apart from almost everything else. Every constraint became a design element. Every problem fed a solution somewhere else in the system. Now let's talk about what it actually felt like to fly this aircraft, because the operational environment was unlike anything that existed before or since. Takeoff in the SR-71 was deceptively ordinary. The aircraft was heavy with fuel, often near its maximum gross weight, and acceleration was gradual by fighter standards. But once airborne and climbing toward the tanker, the mission clock started. After refueling, topping off the tanks that had leaked during taxi, the aircraft accelerated through Mach 1 with almost no drama. The sonic boom from inside the cockpit was nothing. Pilots described passing Mach 1 as less noticeable than a bump in a road. The aircraft was designed to pass through it cleanly, and it did. The violence of the sound barrier existed only for observers on the ground far below. Mach 2 came quickly. Then the inlet spikes began translating, moving aft to optimize the shockwave position, and the aircraft's character shifted. At Mach 3.2, the SR-71 sat in what pilots called the corridor, a narrow band of speed and altitude where every system was in perfect balance. Too slow and the aerodynamics degraded. Too fast and the thermal and structural loads exceeded limits. From 85,000 feet, pilots could see the curvature of the Earth. The sky above was not blue. It was indigo, darkening toward black at the zenith. Stars were visible in daylight, not faintly, clearly. Meanwhile, the airframe around them was glowing. Not in any dramatic visible sense. Titanium doesn't turn red at 600 degrees, but the aircraft was radiating heat in the infrared spectrum, shedding energy in every direction. The 2 crew members, pilot up front, reconnaissance systems officer behind, were sealed in a pressurized cocoon inside a machine operating at the boundary of what the atmosphere allows. The RSO managed the sensor suite, cameras, SIGINT equipment, radar systems, all operating in the same thermal environment, all engineered to function at temperatures that would destroy conventional electronics. The reconnaissance cameras aboard a fully loaded SR-71 could photograph 100,000 square miles of territory in a single, hour-long pass. from the edge of space, moving at over 1/3 of a mile per second, and the images were sharp enough to count vehicles on a road. But the aircraft's greatest defensive weapon wasn't a missile, or a jammer, or any weapon system at all. Speed. In its entire operational history, the SR-71 was fired upon by surface-to-air missiles more than 1,000 times, not dozens, not hundreds, over 1,000 missile engagements across its career. 0 hits. Not because the aircraft had some magical evasion system, because by the time a missile's guidance system computed where the SR-71 was, the aircraft had already moved far outside the missile's engagement envelope. It was simply going too fast to be caught. The standard crew response to a missile launch warning: accelerate. Not maneuver, not jink, not deploy countermeasures, just go faster, because faster was always the answer. Now let's address the question underneath everything we've covered so far. Why did the program end, and why has nothing replaced it? The SR-71 was officially retired in 1990, briefly reactivated in 1995, then retired permanently in 1998. The official reason? Cost. Each SR-71 flight hour cost approximately $200,000 in 1990. The pre-mission preparation, suits, tanker support, ground crew added substantially to that figure. Running the fleet was genuinely expensive. But cost alone rarely ends a program that uniquely fills a critical intelligence mission. The deeper answer is satellites. By the late 1980s, American reconnaissance satellites had advanced to the point where they could cover most of the target sets the SR-71 was being used for, at lower recurring cost and without the geopolitical friction of overflying sovereign airspace. But satellites have predictable orbits. Any adversary with basic astronomy can know exactly when a satellite will pass overhead and conceal activity accordingly. The SR-71 could be over any target on Earth within hours, with no predictable pattern. That tactical flexibility was irreplaceable, and it was the same argument that was made when the program was being canceled. The Air Force, under Secretary of the Air Force Donald Rice, wanted the SR-71 gone. The CIA and DIA, who actually used the intelligence it produced, wanted it kept. Congress sided with the Air Force. Twice. The aircraft that had never been touched by a missile was retired by budget politics. There is a specific irony there that the engineering history of the program probably deserves better. Now the harder question. It has been over 30 years since the SR-71 last flew operationally. Why has nothing replaced it? Part of the answer is that the mission changed. Satellites and long-endurance unmanned aircraft like the Global Hawk can loiter over an area for 20 hours. The SR-71 could not loiter. It could only pass through at Mach 3. But the deeper answer is about what it actually costs to build and operate an aircraft in that speed regime, and whether any organization has been willing to pay it since. Building one SR-71 required inventing titanium machining as an industrial discipline. The manufacturing knowledge was so specialized that it lived almost entirely inside the Skunk Works organization. When the program ended, much of that knowledge was retired with it, not destroyed, but distributed, dispersed, no longer held as a living institutional capability. Lockheed's own engineers have stated that rebuilding the SR-71 today, not a new aircraft, the same aircraft, would cost more in modern dollars than it cost to build the entire original fleet, because the baseline industrial knowledge would have to be reconstructed from scratch. There are programs in development. Lockheed's SR-72, a proposed successor that would reach Mach 6, has been in varying states of concept development since roughly 2013. Mach 6. The SR-72 would need to solve every problem the SR-71 solved, and then solve an entirely new set that the SR-71 never had to touch. At Mach 6, titanium doesn't survive either. Carbon composites and ceramic matrix composites would form the structural skin. The propulsion system, a combined cycle engine blending a turbine and a scramjet, has never been demonstrated in operational flight. The SR-72 faces the same fundamental paradox the SR-71 faced 60 years ago. Existing materials and manufacturing cannot support the design. The design is ahead of the industry. The SR-71 resolved that paradox by forcing the creation of an entirely new industrial capability. The question for the SR-72 is whether anyone will fund the same process again. Let's close by going back to the records, because the numbers deserve full context. On July 28, 1976, SR-71 serial number 17972 set the absolute airspeed record for a sustained level flight aircraft, 2,193.13 miles per hour. That record has not been broken. On the same day, the same aircraft set the sustained altitude record for a horizontal flight, 85,068.9997 feet. That record has not been broken either. In 1990, on its retirement ferry flight from Los Angeles to Washington, D.C.'s Dulles Airport, an SR-71 crossed the continent in 64 minutes and 20 seconds. That cross-country speed record also still stands. These are not historical artifacts. They are current records, active, unbroken. Every aircraft designed after the SR-71, every modern fighter, every stealth aircraft, every supersonic business jet concept is slower. None of them have cleared the bar set in 1976 by an aircraft that first flew in 1964. Why? The honest answer is that the world chose different priorities: stealth over speed, precision munitions over penetrating altitude, unmanned endurance over manned performance extremes. Those are rational choices, but they are choices. The SR-71's records stand not because they are impossible to break, they stand because nobody has decided it is worth trying. And that distinction matters. An unbroken record isn't always proof that a thing is impossible. Sometimes it's proof that we stopped trying. The SR-71 was designed by a small team operating under conditions of extraordinary secrecy, with no precedent to draw from, using a material the industry barely knew how to machine. They built 32 aircraft. They flew for over 3 decades. 12 were lost, all to mechanical failure or accidents, not one to enemy action. That is a remarkable operational record for an aircraft operating permanently at the absolute edge of what physics allows. The aircraft didn't succeed, despite its engineering contradictions. It succeeded because of the way those contradictions were resolved, each one feeding a solution into the next problem. The leaking fuel became the cooling system, the thermal expansion became the sealing mechanism, the ram air that threatened to destroy the engine became the primary source of thrust. Heat, the enemy, was harvested and put to work. That is what makes the SR-71 worth studying. Not the records it set, not the missions it flew, not the flag it flew under, the machine itself, the logic of how it was built, the audacity of what it asked materials and physics to do, and how completely it got away with it. If you found the engineering in this video interesting, the next logical step is understanding the aircraft that tried to do what the SR-71 did, from a different angle entirely. We have that video queued up. It's worth your time.